Question number 1 to 6. The strain energy stored in a member is given by option C is right answer. Half into stress into strain into volume of the member. Question number 1 to 7. A rectangular block of size 200 mm into 100 mm into 50 mm is subjected to a shear stress of 100 Newton per millimeter square. If the modulus of rigidity of material is 1 into 10 to the power 5 Newton per millimeter square, the strain energy stored will be. We know the formula for strain energy U is equal to tau square by 2g into V. Tau is the volume of the block and tau is the shear stress. G is the modulus of rigidity of the material and V is the volume of the block. So volume of the block will be length breadth into height. So volume will be equal to 200 into 100 into 50 m3 and G and the value of G and V tau is given in the question. So if we put all the value in this equation of strain energy, we will get strain energy U equal to 5000 Newton millimeter or 50 Newton meter. Option C is right answer. Question number 1 to 8. A steel rod of cross sectional area equal to 1000 millimeter square is 5 meter long. If a pull of 100 kilonewton is suddenly applied to it, then the maximum stress intensity will be. The maximum stress value equal to 2 into P by F, where P is the suddenly applied load and A is the cross sectional area of the rod. So cross sectional area of the rod given in the question 1000 millimeter square and suddenly applied load is 100 kilonewton. That means 10 to the power 5 Newton. So if we put the value in this equation, tau max, the stress will be equal to 200 Newton per millimeter square. Option C is right answer. Question number 1 to 9. In two circular bar A and B of same material and same length are of diameters dA and dB respectively. The bars are subjected to same torque T. The ratio of strain energy stored in the bars A and B is proportional to. We know the formula for strain energy U equal to T square L by 2GJ. T is the applied torque, L is the length of the bar and G is the modulus of rigidity and J is the polar moment of inertia, which is equal to pi d to the power 4 by 32. So from this equation we can write strain energy U is inversely proportional to 1 by polar moment of inertia of the bar. That means strain energy will also be inversely proportional to the 1 by d to the power 4 diameter of the bar. So we can also write the strain energy of the material of the bar A divided by strain energy of the bar B equal to diameter of the bar B divided by diameter of the bar A to the power 4. Option D is the right answer. Number 130. Two identical bars, one simply supported and other fixed at ends, are acted upon by equal loads applied at the midpoints. The ratio of strain energy stored in simply supported beam and fixed ended beam is. So for a simply supported beam subjected to central point load P, the deflection at the center will be equal to PL cube by 48 EI, and the strain energy formula U1 will be equal to half into the load P into deflection del 1. And when the beam is fixed beam and subjected to central point load P, the deflection will be at the center PL cube by 192 EI, and the strain energy formula U2 will be equal to half into load P into del 2. This is equation 1, this is equation number 2. So strain energy U1 by strain energy U2 will be equal to 4. Option D is right answer. Question number 131. If the depth of a beam of a rectangular section is reduced to half, the strain energy stored in the beam becomes. We know the formula for strain energy U equal to integration m square dx divided by 2 EI. M is the bending moment at the corresponding section. E is the modulus of elasticity and I is the moment of inertia of the beam section. So we can write from this equation strain energy U is inversely proportional to the moment of inertia of the section of the beam. Now if the diameter gets half, that means D dash equal to half into D. So I dash will be equal to 1 by 2D cube. That means 1 by 8 into D cube, because we know I equal to BD cube by 12. So from this I is proportional to the D cube. So if we calculate, U dash will be equal to 8 into the initial strain energy. D is right answer. Question number 132. The system which is shown in the figure 10.10 consists of two prismatic bars of same length L and same axial rigidity AE. The system lies in the vertical plane and carries a vertical load P at joint X. The vertical deflection of the joint X is, say the member force in AX and BX is T. So 2T sin 30 is equal to P by the component of force. So by the component of force 2T sin 30 will be equal to the vertical diagonal load P, and if we calculate T will be equal to P. So strain energy for the two member AX and BX will be equal to U equal to 2 into for the 2 into P square L by 2 AE. And by Castigliano's second theorem we know the vertical deflection at a point X is equal to partial derivative of the strain energy with respect to the load. Okay, so del Vx will be equal to del by del P into the strain energy value P square L by A. And if we do that, and if we calculate, del Vx will be equal to 2PL by A. Option C is right answer. Question number 133. The specimen in a Charpy impact test is supported as simply supported beam. Option B is right answer. Number 134. Impact test enables one to estimate the property of toughness. Option B is right answer. Question number 135. The phenomenon of decreased resistance of a material to reversal of stress is called fatigue. Option B is right answer. And the failure by this phenomenon of a material is called fatigue failure of the material. Question number 136. The property of a metal which allows it to deform continuously at a slow rate without any further increase in stress is known as creep. Option B is right answer. 137. The stress below which a material has a high probability of not falling under reversal of stress is known as endurance limit. Option D is right answer. Question number 138. A three-hinged parabolic arch reeve is acted upon by a single load at the left quarter point. If the central rise is increased, the shape of the arch altered to segmental without changing the other details. The horizontal thrust H will be equal to MC by small h. Small h is the central rise of the arch, and MC is the bending moment at the ground if the arch is simply supported beam. So from this equation we can write horizontal thrust H is inversely proportional to the rise of the arch, central rise of the arch. Option B is right answer. Question number 139. For ductile materials, the most appropriate failure theory is. Option D is right answer. Shear strain energy theory. Number 140. At a point in a steel member, the major principal stress is 2000 kg per centimeter square and the minor principal stress is compressive. If the uniaxial tensile yield stress is 2500 kg per centimeter square, the magnitude of the minor principal stress at which yielding will commence according to the maximum shearing stress theory is. According to Tresca's theory, yielding occurs when sigma 1 minus sigma 2 equal to Fy. Sigma 1 is the major principal stress and sigma 2 is the minor principal stress, and Fy is the yield stress of the material. So sigma 1 is equal to 2000 kg per centimeter square and Fy yield stress is equal to 2500 kg per centimeter square. And if we calculate, sigma 2 will be equal to 5 minus 500 kg per centimeter square. So negative means compression. Option D is right answer. For the design of a cast iron member, the most appropriate theory of a failure is Rankin's theory. Option B is right answer. 2. Consider the following statements. In a unidimensional stress system, the principal plane is defined as the one on which the shear stress is 0 and normal stress is maximum. Option C is right answer. 143. If an element is subjected to pure shearing stress tau xy, the maximum principal stress is equal to, in case of pure shear, sigma s equal to sigma y equal to 0 and tau xy will be equal to tau. Sigma 1 and sigma 2 will be equal to plus tau and sigma 2 will be equal to minus tau. Option C is right answer. 144. A steel cable of 2 cm diameter is used to lift load of 500 pi kg. Given that Modulus of elasticity E equal to 2 into 10 to the power 6 kg per centimeter square, and the length of the cable is 10 meter. The elongation of the cable due to the load will be, we got the diameter of the cable 2 centimeter, load 500 into pi kg, modulus of elasticity E equal to 2 into 10 to the power 6 kg per centimeter square, and length of the cable 10 meter equal to 1000 centimeter. The formula for elongation del L equal to PL by AE. A is the cross sectional area of the cable, so A will be equal to pi by 4 into d square, and A will be equal to pi centimeter square, and del L is equal to, by putting all the value, 0.25 centimeter. And B is right answer. 4.5. A mild steel bar is in 3 parts, each 20 centimeter long. The diameters of the parts AB, BC and CD are 2 centimeter, 1 centimeter and 3 centimeter respectively. The bar is subjected to an axial pull of 4 ton as shown in the figure 10.11. If modulus of elasticity E equal to 2 into 10 to the power 6 kg per centimeter square, and the elongation in the 3 parts of the bars are del 1, del 2 and del 3 respectively, the ratio of greatest to the least of this elongation will be, the formula for elongation del L is equal to PL by AE. P is the load, L is the length of the member, and A is the cross-sectional area of the member, and E is the modulus of elasticity of the member. Okay, and we know the formula for cross-sectional area. A equal to pi by 4 into d square. D is the diameter of the member. So we can write del L is inversely proportional to the 1 by d square. This is our fundamental equation. Okay, so for the part AB, del L AB, the diameter is given 2 centimeters, so 1 by 2 square equal to 1 by 4. Del L BC, for the part BC, the diameter is given 1 centimeter, so the elongation BC will be 1, and elongation C at CD will be equal to 1 by 3 square, because diameter is given 3 centimeters, so 1 by 9. So the greatest elongation will be 1 centimeter, and the least elongation will be 1 by 9 centimeter. So if we make the ratio del L BC by del L CD, we will get the ratio 9. A is right answer. 146. A steel bar of 2 meter length is fixed at both ends at 20 degrees Celsius. The coefficient of thermal expansion is 11 into 10 to the power minus 6 per degree Celsius, and the modulus of elasticity is 2 into 10 to the power 6 kg per centimeter square. If the temperature is changed to 18 degrees Celsius, then the bar will experience a stress of, length of the steel bar is equal to 2 meter, that is cooled from 20 degrees Celsius to 18 degrees Celsius. Okay, so the difference in temperature del T will be equal to 2 degrees Celsius, and the linear coefficient of thermal expansion alpha is equal to 11 into 10 to the power minus 6 per degree Celsius, and modulus of elasticity of the bar is equal to 2 into 10 to the power 6 kg per centimeter square. And we know the formula for thermal stress, sigma T is equal to alpha into del T into E, and if we put all the value in this equation, we will get sigma T is equal to 44 kg per centimeter square, that is in tensile. Option D is right answer. 147. A cast iron block of 5 square centimeter cross section carries an axial tensile load of 10 ton. Then the maximum shear stress in the block is given by, the normal stress for the block sigma will be equal to P by A. So P is equal to load 10 ton equal to 10 into 1000 kg, and the area of the block is 5 square centimeters. So if we calculate sigma n, normal stress will be equal to 2000 kg per centimeter square, and maximum shear stress tau max will be equal to normal stress by 2 for axial loading. So 2000 by 2 equal to 1000 kg per centimeter square. Question number 148. An elastic bar of length L, cross sectional area capital A, Young modulus of elasticity capital E, and self weight capital W is hanging vertically. It is subjected to a load of P applied axially at the bottom end. The total elongation of the bar is given by, the elongation due to load P will be PL by A, and the elongation due to self weight W will be equal to WL by 2AE. So total elongation del L will be equal to WL by 2AE plus PL by AE. Option B is right answer. Question number 149. A long construction member of uniform section is to be lifted using ropes at C and D. See the figure 10.12a. This causes bending moment due to self weight as shown in the figure 10.12b. To minimize the peak value of bending moment, the overhanging portion B shall be such that to minimize the peak bending moment value that will be at the center E, the positive bending moment at the center E should be equal to the maximum negative bending moment at C and D. Suppose say self weight of the member is equal to W per unit length. So bending moment M1 will be equal to W into B square by 2 minus, because this is hogging, and the bending moment, positive bending moment at the center M2 will be equal to W into this length L minus 2B square by 8 minus the hogging moment WB square by 2. And as per question, the answer is mod M1 equal to mod M2. That means irrespective of the nature of the moments, these two moments are equal to each other. And if we calculate the overhanging span, this portion B and this portion B will be equal to 0.207 L. Option B is right answer. Question number 150. Consider the following statements with reference to a continuous beam supported at A, C and E for which the shear force diagram is shown in the figure 10.13. If there is vertical jump in shear force diagram, that means there is point load. Okay, and if the sloping straight line is there in shear force diagram, that means there is UDL in that portion, and if there is curved line in shear force diagram, then UVL load is there. From this diagram and our rules, we can say there is a concentrated load acting at the point B and a uniformly distributed load acting on the portion CE, because sloping straight line is there and vertical jump is there at point B. That means point load at here, and sloping straight line means the UDL from is there from the portion C to E. So option D is right answer.